This lesson will be examining geometric sequences. A geometric sequence is a pattern of numbers that has a constant ratio or multiple between terms. Sometimes that ratio makes things bigger, sometimes it can make things smaller. So if we look at the first example here in the red, this is geometric because between 3 to negative 9 to 27 to negative 81, we're always multiplying by negative 3. It's making it bigger. It's also changing the signs, and that's okay. We can alternate signs. In the second one, we go from 4 to 2 to 1 to a half. Our R value this time, our ratio, is we're always multiplying by a half. Half of 4 is 2, half of 2 is 1, half of 1 is a half, and so on and so on and so on. So those are considered geometric sequences. Non-geometric sequences, they may have a pattern to them. So for example, this one here involves exponents. 1 squared, 2 squared, 3 squared, 4 squared, and so on. Well, those aren't a constant multiple. You can't multiply by the same number each time to go from 1 to 4 to 9, and so on. The next one, 4 times 4 makes 16. That looks good. 16 times 16 makes 256. That's a different multiple. So as soon as I change my multiple, even though the fact later on this one comes back to 4 again, the fact that I have a different multiple in the middle there means that this is not a geometric sequence. It has to be the same multiple every single time. And like arithmetic things, once we figure out they're geometric, we can make a general term, an equation that defines this. So the general term for a geometric sequence looks a little bit different. We still have un, we still have u1, but now we have an r for our ratio, and it's to an exponent. How many times do you need to multiply by r? Okay, so the n minus 1 is our exponent this time. So other than the r and d difference, the letters are the same, we're going to apply them in a slightly different way. To find r, you can find the difference between u2 and u1 as a ratio. So divide them. That will give you your r every time. But if you don't know u2 and u1, you can actually find the difference between any two consecutive terms. So u10 divided by u9, u100 divided by u99. As long as they're consecutive, the ratio between them, the multiple, will always be your r value, if you know it's geometric. So let's try a couple. State the general term, the equation for each sequence. So un equals u1 times r to the n minus 1. So if we look at the first one here, our first term is 5. Our ratio, if I want to figure it out, I take my second term divided by my first term. In this case, 25 divided by 5. That'll be my r value to the power of n minus 1. And here's the nice thing with geometric sequences. They don't require simplifying. You're done. That's it. Stop there. Okay. Try the second one. un equals u1, 10, times r. R is going to be negative 1, that's u2, divided by u1. Oh, well, negative 1 divided by 10 is 0.1, and it's negative. That's okay. N minus 1. Done. Whenever you have a negative base, that just means you're going to alternate numbers when you look at the sequence. So positive, negative, positive, negative, positive, negative, and so on. All right, we'll try one more. Fraction one this time. Fractions can often be messy. Okay, let's get it set up. un equals u1 times r. Now r this time, I got to do 1/9 divided by 1/27. I can use my calculator to do that if I want to, or think of it as fractions. 1/9 divided by 1/27. If I divide fractions, I flip and multiply. Oops, 21 over 1, which gives me 27 over 9, or in other words, 3. Same thing your calculator would give you. And if you actually happen to look later on, you notice this is 3 times as big, 3 times as big. What's the next pattern? 3. And our exponent, n minus 1. There's our general term. We don't have to simplify these ones, okay? The reason we don't is because BEDMAS says do exponents before multiplying. And our exponent's unknown. It's a variable, so we can't apply it until afterwards. So let's work with a sequence this time. So I've got a sequence, 8, 4, 2, 1. Find un. Find our general term. Okay, we can do that. u1. u2 divided by u1 is 4/8 or 1/2. I'll use 1/2 to the power of n minus 1. Done. Part B. Let's find u10. Let's use our equation we just built. So 8 times 1/2 to the power of 10 minus 1. If you want to, you could use fractions here. You can use decimals here. I'm not really picky. Either one. Most of our calculators are probably going to flip it to a decimal because it's such a big number. But you have to be exact if you're using decimals. 1, 5, 6, 2, 5. Keep all the decimals. You can't round it off. All right, part C. If the last term of the sequence is 1 over 256, how many terms are there? So I know the last term. I know UN. I know the first term. I know the R. I don't know the exponent. I want to solve this. So to solve this exponential equation, because I know it's going to come out to a whole number, and I know that because it's a member of the sequence, I can actually solve this using a mathematical method as opposed to technology. Here's how we're going to do that. We're going to make it simpler first of all. We're going to divide out the 8's. If I divide one side, I got to divide the other side. So 1 over 256 divided by 8, either a big long decimal, and you're welcome to keep the big long decimal, or a fraction that keeps the entire fraction. Some calculators can't handle the fraction, so I will write out the big long decimal. 0, 0, 0, 4, 8, 8, and it actually keeps going, right? We want that whole decimal. And I'll be left with 0.5 to the n minus 1 on this side. Now here's the tricky part. You actually have to guess and check. You've got to figure out, on the left-hand side, we're going to keep the rate the same, but on the left-hand side, what number, as an exponent, will keep this, will make this. I got to guess and check. 0.5 to the 1, 0.5 to the 2, 0.5 to the 5, 0.5 to the 6. What number actually makes 0.5 to the what? Come out to that big long decimal. And if you try it, you should get 0.5 to the 11. Comes out to the exact same decimal that we saw earlier when we divided 1 over 256 by 8. Right? There will be a number. It has to be a number because it's a member of our sequence. Here's your nice next little trick. If our bases are the same, and they are, that means the exponents have to be the same. In other words, 11 equals n minus 1, or n is 12. And that's how we can solve these exponential equations, by guessing and checking a little bit. Now, if you have technology, you could use that too. This would be y1, this would be y2, or up here y1, y2, and solve it. That would work totally fine. But we can solve it by hand because we know it has to be a known number. I'll try another one in just a second here, okay? A geometric sequence can be defined by this general term. Determine the first 5 terms of the sequence. Now, it's really nice doing geometric ones because you know the first term. It's -3. And you know how you can get to each term after that by multiplying by r. What's -3 times 5? -15 times 5. -75 times 5. -375 and times 5, -1875. Geometric sequences are really quick to figure them out. Okay, if I want to find u9, I can do that. -3 times 5 to the 9 minus 1, or in other words, to the 8. If I do that, I get a really big number. Geometric sequences are really big usually because they grow so fast. They're exponential. Okay, part C. The sequence contains the number -234, 375. -234, 375 is a number in our sequence. I want to know what number is it. So I'm going to set it equal to my equation. Here's where we're going to use that guess and check strategy again. To do it, I first have to get rid of that -3. I need to have one base on each side. So if we divide this, we end up with 78,125 equals 5 to the n minus 1. So guess and check, 5 to the what makes this? I'm going to keep the right hand side the same. Guess and check, I get 5 to the 7, comes up to 78,125. If my bases are the same, my exponents are the same. So I can say this is the 8th term. And I will guarantee the guess and check has to work if the member is a sequence, and they're telling us it is. The last term, 29 million. How many terms are in the sequence? Well, let's take part C all over again, right? Just figuring out the last term this time. So -29,296,875 equals -3, to the 5, or sorry, times 5 to the n minus 1. divide out that 3. That negative 3 makes it a positive 9, 7, 6, 5, 6, 2, 5. Guess and check. 5 to the what? Turns out it's 5 to the 10. Base is the same. Exponent's the same. There's 11 terms in that sequence. You know, I could have done it, I suppose, but I keep typing my calculator times 5, times 5, times 5, times 5, times 5. And I started the sequence. Eventually, I would have got there too, but then I have to figure out how many times I multiply by 5, right? And the formula is a little bit faster. And last thing, in a geometric sequence, the third term is 0.5 and the seventh is 40.5. Find an equation for this sequence. So what do we know? We know that U3 is 0.5, and we know that U7 is 40.5. Now, because they're not consecutive, I can't find out R directly, but I can solve for it. I can take U3 and turn it into an equation. The equation will be U1 times R to the 3 minus 1. And I simplify that, I get U1 R squared. If I do the same thing with my second equation, 40.5, U1 R to the 7 minus 1, I get 40.5 equals U1 R to 6. If you remember last time we talked about arithmetic sequences and we had to have a situation like that, we were allowed to use elimination. Well, we can kind of do the same thing here. I'm going to take the equation with a bigger exponent and write it on top. I'm going to take the equation with a lesser exponent and write it on the bottom. But I'm not going to subtract to eliminate. Instead, I'm going to divide. And when I do my division, 40.5 divided by 0.5 comes out to 81. U1 divided by itself is gone. And when I divide bases that are the same, I will subtract their exponents. That's how we divide bases that are the same. So we'll get R to the 4. How do I solve for R? I take the fourth root of 81. Now here's one little tricky bit. The number is 3. Because the fourth root is an even number, I don't know if I'm alternating signs or not. So I have to put in a plus minus. It only happens if there's an even nth root. If it's odd, I know what it is. I'm not alternating anymore. I can see it. If it's even, I don't know if it goes positive, negative, or if they're all positives. So I have two situations I have to solve here. I got to figure out if R is 3, what happens, and if R is negative 3, what happens. Either way, I can use my equation from way back up here to solve for U1. So let's do that. We know 0.5 equals U1 R squared. So let's see what happens if R is 3. We'll get 0.5 equals U1 times 3 squared, which is 0.5 U1 times 9. That means that U1 is 0.5 divided by 9. Now, I don't really like that number, so I'm going to turn to a fraction. 0.5 is a half. A half divided by 9 really makes 1/18. So if R is 3, my equation will be 1/18 times 3 to the n minus 1. Let's see what happens if R is negative 3. Same style of question, same solving procedure. Only difference is I have a negative 3 in there. Well, something kind of nice happens this time. It won't always happen because I have a nice exponent there. But negative 3 squared comes out to 9. And I've seen this answer before. I know that if I divide this by 9, I end up with 1/18. So either way, U1 has to be 1/18. I just don't know what happens in the middle, if it alternates signs on the even numbers or not. Okay, but I do have to write down both. I don't have a choice on that. There's part A. There's two answers to it. Part B asks, what happens? Oh, no, find the 10th term. So let's do that. And how many choices are there? Well, there's 2 of them. All right, so we need to find U10. U10 this way will give me 1/18, 3 to the 10 minus 1. Into my calculator, I go with that. I end up with 1093.5. Or U10, because I don't know, Could be, well, what happens if it's a negative 10 in the middle? So if I do this one, I get the same number, but I get the opposite sign. And that's our issue here, right? We don't know if it's an alternating sequence or a constantly positive sequence. So we have to solve it as if it could be both. Those are geometric sequences. Okay? We're solving for them, using them, finding terms. Guess and check is a valuable strategy if you don't have a calculator. And we should be able to do a little bit of problem solving. Here's some homework to try. Don't do the stuff that's recursive. Just find me the general term. And then if you're stuck, come see me.